This is AP Physics B to 1992 exam questions, free response question. A spacecraft of mass 1,000 kilogram is in an elliptical orbit about the Earth as shown above. At point A, the spacecraft is at a distance of RA. So here is, they do it between the centers of the mass, RA. 1.2 10 to the 7 meters from the center of the Earth, and its velocity of magnitude VA, and the velocity is always perpendicular to the radius or the tangent line to the circle, touches at one point, meters per second, is perpendicular to the line connected to the center of the Earth to the spacecraft. The mass and the radius of Earth are given, and I wrote for you everything on the side. Determine each of the following for the spacecraft when it is at point A. So in A, they ask you to find the total mechanical energy of the spacecraft, assuming that the gravitational potential energy is zero at an infinite distance from the Earth. Before we use the gravitational potential energy of the object that is moving away from Earth, I want to explain the understanding of the formula of the gravitational potential energy. So if I have our planet Earth and the distance this is the center of the mass, the farther and farther away I take an object, the less and less potential, I do not want to say less and less potential energy. Let's say it this way. As if I take an object far, far away from Earth, its potential energy to do work on that object is going to be equal to zero. And sometimes instead of using potential energy formula or the letters that I use usually in the classroom, they often use the U for potential energy. So I'm going to use what they usually use, the U. In this case, so the potential energy far, far away from Earth would be zero, because Earth does not have enough strong force to bring it back. It doesn't have enough force to convert this potential energy to the kinetic energy. So I will assume the potential energy is equal to zero. Now, if I bring this spaceship or craft or whatever that is, object, closer to Earth, and it has a mass m, and it's going to be the distance away from Earth this much, then the potential energy is equal to, and we know that the work is equal to the change of the potential energy or kinetic energy, which is the force times the distance. And in this case, the force is gravitational force, so I have G mm over r squared times the distance, how far it is away from the Earth. And I can cancel r, so I have the gravitational potential energy at this point is equal to G mm over r. M, the mass of the Earth, and little m is the mass of the object. But also, if I assume that I look at the potential energy at the center of Earth, the distance away from Earth, potential energy, another formula that you know, is equal to mgh, right? This is how far I take an object away from the surface of Earth. But when it comes to far, like the space distances, so we're looking at the different formula, the one that I'm deriving right now, or explaining. So if h is close to the center of the Earth, then the potential energy is also equals to zero. The farther and farther away I take the object, the more of this potential energy is going to be turned to the kinetic energy, and the work is done. So if the energy, when I take an object away farther and farther away, if I don't place, let me say this way, if I don't place this negative sign over here, then if this is my final destination at the end where I have infinity, and this is my initial destination, the change of energy is going to be the final minus initial and will give me a negative number. So I have to keep this negative number. It's many different books have a different explanation. I find this is the easiest to explain this way. So if you take it far, far away, this position minus this position would give you a negative number. So the infinity position minus this position. So if an object is taken away from here that way, the potential energy should increase. The final minus initial should be equal to positive number, but it will give you a negative number. But if the final is 0 minus initial, which is this one, then it will give you a positive number. So the potential energy increases when you take it farther and farther away. But it assumed by the definition that the potential energy of the object when it's taken to the infinity is equal to 0, because no work can be done on the object to bring it back and convert it into the kinetic energy. But the formula that I have to use is this one. So I'm going to be using for potential energy when I take the object away, negative g mm over r. So one of the r's cancelled, and I have negative g mm over r. So the total mechanical energy is the sum. So the mechanical energy, sometimes you will see something written like this, mechanical energy or energy, the total mechanical energy is equal to the potential energy of the object plus the kinetic energy of the object. And that's going to be the energy at point A. So I have negative g, m of Earth, mass of the satellite, over r, the distance, and that's going to be RA, plus the kinetic energy is 1/2 m, and the velocity of A squared. And if I plug in my numbers, I have 6.67 negative 10 to the negative 11. The mass of Earth is 6, 10 to the 24. Mass of the satellite is 1000. Divided by the radius or the distance, to the satellite, which is 1.2. 10 to the 7, and plus 1/2 the mass of the satellite, again 10 to the 3rd, and the velocity of the satellite at point A is equal to 7.1, 10 to the 3rd, and all of it squared. And my answer is, so the first number is 33.5, 10 to 9th, plus the second number is 25.2, 10 to the 9th, and the first number I forgot to write. The first number is negative. So my answer is negative, let me see, 8.3, negative 8.3, 10 to the 9th joules. So that's my answer for A. For B, they ask you to find the magnitude of the angular momentum of the spacecraft about the center of the Earth. So the angular momentum, if you remember from the lessons, is equal to L. And if linear momentum is equal to mass times velocity, angular momentum has the same formula, just different letters and different meaning. So you have, instead of the mass for rotational motion, we use inertia, and angular velocity. Because it is the center and the object is rotating around its axis, it's the same as if we had a hoop. So you don't have to memorize these formulas. Usually they will give it to you it's good to remember a few of these formulas. And if you remember from the lesson that I posted for you, it's good to remember if you have a disk filled in with stuff, its inertia is equal to 1/2 mr squared. And if you have a hoop, its inertia is mr squared. So these two is very good to remember. I haven't seen them ever in the formula sheets, but it looks like here they want you to know this formula. So for this one is like a hoop. So you have mass of the spacecraft, and then the distance for the mass, how far it is from the spacecraft, and times the angular velocity. And if you remember again that the linear velocity is equal to radius times the angular velocity. So if an object is rotating in a circular motion, the object that rotates closer to the center rotates at lower linear speed than the one is farther away. And it depends, so they both can make this angle at the same angular velocity. So in 1 second, let's say, they both can be in this position. So they both move the same angular distance, but they don't move, or theta, which is angular distance, right? But they don't move the same linear distance. This one moves bigger distance than this one moves. So the tangential velocity that is perpendicular has a relationship between the angular velocity and tangential velocity. So tangential is equal to r times velocity. So if you remember this formula, I'm going to use it right now. So in this case, you have mass times RA, and one of the RA I'm going to combine with the angular velocity. That gives me linear velocity, which is velocity at A. And if I plug in these numbers, looks like I am going to have 8.5 10 to the 13, and that is kilogram. It is kilogram meters squared over seconds. So kilogram meters squared over seconds. Later, the spacecraft is at point B on the exact opposite side of the orbit at the distance RB meters from the center of the Earth. Determine the speed of VB of the spacecraft at point B. So you have some potential energy and some kinetic energy here. You have the total mechanical energy that we calculated. So this is the total mechanical energy of the system. And if you know, the mechanical energy of the system is not going to change no matter where the object is. So if I can calculate the potential energy of this object and subtract it from the mechanical energy, I will know how much kinetic energy is left. So, and from there I can figure out the speed. So I'm going to come back right here, and I'm going to say the potential energy of the object. The potential energy of the object at that position is negative g m of the Earth, m of the spacecraft, over rb. That gives me negative 6.7 or 67, 10 to the negative 11. The mass of the Earth, 6, 10 to the 24. The mass of the satellite or spacecraft is 10 to the 3rd. And RB, they give you 3.6, 10 to the 7. So my new potential energy is equal to, I should write it more like a U, not a velocity. So that is equal to negative 11.2, and that is 10 to the 9 joules. So So my total energy must be equal to this number, and I only have this number. So I need the kinetic energy must be equal to the difference between those two. It will give me 2.9 10 to the 9 joules. And they ask me the speed of VB. So kinetic energy is equal to 1/2 mass velocity at B squared, and equals to 2.9 10 to the 9th. So I have VB is equal to the square root of 2.9 10 to the 9 times 2 divided by the mass, which is 10 to the 3rd. So my velocity at B is equal to 2.4 10 to the 3rd meters per second. So this is my velocity of an object at point B. For D, they say, suppose that the different spacecraft is at point A at distance r equals 2. So here they give you the distance, meters away from the center, so the same distance from the Earth. The speed of the craft, determine each of the following. The speed of the craft if it is in a circular motion around the Earth. So if it is a circular motion, then your force of gravity is equal to your centripetal force. The force of gravity is G mm over r, in this case squared. It's the gravitational force is equal to centripetal force, which is m v squared centripetal acceleration over r a. So in this case, I can cancel m and m in one of the RA's. And I'm gonna get velocity at B is equal to the square root of G, mass of the Earth, over RA. And if I plug in my numbers, G is a gravitational constant, 6.7 10 to the negative 11. Mass is 6 10 to the 24, and the distance is given 1.2 10 to the 7th. So if I plug in these numbers, let me see what I'm gonna get. Looks like it's gonna be 5.8 10 to the 3rd meters per second. So that would be my answer for D. For E, they ask you the minimum speed of the spacecraft at the point A if it is to escape completely from the Earth. So I'm going to explain to you escape velocity, how to derive it, and what it means. So if I have an object that is on the surface of the Earth, and I'm going to give it some kinetic energy. So this object will get to a certain height and lose all this kinetic energy to the potential energy. But at this moment, the object should have no energy left. So that means no energy to bring it back to Earth, so it escapes. So that means the kinetic energy is all going to be converted to the potential energy, or kinetic energy plus the potential energy must be equal to 0. And this is how I'm going to start this question. So I'm going to say the kinetic energy, or the potential energy, negative G mm, let's keep it the same as we have been, negative G mm over R In this case, it's the on the surface of the Earth, and mass of the Earth, mass of the spacecraft, plus the kinetic energy, which is 1/2 m, and this is going to be the escape velocity, equals to 0. So if I set them equal to each other, I have g mm over r, and this is the Earth, is equal to 1/2 m and the escape velocity squared. And again, mass and mass can be cancelled. That means it doesn't depend on the mass. The escape velocity does not depend on the mass. And the escape velocity is equal to, and what the does depend on the mass of the planet and the radius of the planet, and g is a constant. So I have the square root of 2 gm over re, and if I plug in my numbers, looks like I'm gonna get 8.2 10 to the 3rd meters.